Have you ever looked at a massive machine, maybe one lifting a car, and just wondered, how? How does that even work? Well, it's not magic, it's physics. And today, we're going to pull back the curtain on this simple but incredibly powerful idea called the liquid lever.
So let's get right to it. Here's the puzzle we're trying to solve. How can a tiny little push, just 20 newtons, which is about the weight of a big bottle of soda, how can that lift something that weighs 400 newtons? That's 20 times heavier. It seems impossible, right? Well, let's find out how it's done.
The answer, the secret sauce, is something called force multiplication. And the tool that lets us do it is a hydraulic press. You can think of it like a lever, for prying something heavy. But this lever, it's made of liquid.
I mean, just look at these numbers. You put in 20 newtons of effort, and you get 400 newtons of raw lifting power out. That is a 20x return on your investment. But that force doesn't just come from thin air. Something very clever is happening inside the machine. And here it is. This is the key. The real secret isn't about transmitting the force directly. It's about transmitting pressure. The liquid inside the system is basically a messenger, and it carries that pressure perfectly from one end to the other without losing a single drop.
Now, this whole idea of transmitting pressure through a liquid, it's got a name. It's called Pascal's principle. And you can really think of it as the secret ingredient that makes this whole liquid lever recipe work.
So what does that actually mean? Well, it's pretty simple. If you take a liquid that you can't really squish, like water or oil, and you push on it in one spot, the pressure you create doesn't just stay there. Nope, it spreads out instantly and evenly to every single part of that liquid.
Okay, so let's walk through it. First, we push down with our small force on a small piston. Let's say it has an area of 10 square centimeters. That little push creates pressure inside the liquid. Now, thanks to Pascal, that exact same pressure travels everywhere and starts pushing up on a much bigger piston, one that's 200 square centimeters. And because that second piston has a way bigger surface area, that same amount of pressure creates a much bigger force on the other side.
And this number right here, this is the hero of our story. That 20 newton push on a 10 square centimeter area creates a pressure of exactly 2 newtons per square centimeter. That pressure is our constant. It's the magic number that gets sent everywhere in the system, and it's what does all the heavy lifting for us. So we get that applying a force creates pressure, but that kind of begs another question, doesn't it? Where does the pressure in a liquid even come from to begin with? It all starts with something super basic, its own weight.
I mean, think about it. If you've ever dived to the bottom of a swimming pool and felt that weird pressure in your ears, you've experienced this firsthand. The deeper you go, the more water there is piled on top of you. And all that water has weight, which pushes down and creates pressure.
This is what we call hydrostatic pressure. It's literally the pressure created by the weight of a column of liquid sitting on top of a point. So naturally, the deeper you go, the taller and heavier that column of liquid is, and the more pressure you're going to feel. Now, the formula for this might look a little intimidating, but it's really not. P is just for pressure. The other parts are just telling us how heavy that column of water is. H is its height or depth. Rho, that's the Greek letter rho, is just its density, or how heavy the liquid is for its size. And G is just the constant pull of gravity. Simple as that. And you can really see this in action here. Just 1.5 meters deep in a lake, you're already feeling 15,000 pascals of pressure. But go down to 10 meters in the sea, and that jumps all the way up to over 100,000 pascals. That's a massive increase, and it's all just from the weight of the water above.
Okay, so this is way more than just a cool concept in a physics book. Now that we've got the principle down, let's look at where this awesome liquid lever actually shows up in our everyday world. You'll be surprised. You've definitely seen these around, from those giant lifts at the mechanic shop to the little jack you might have in your car's trunk, and yeah, even in the system that literally saves your life every time you get behind the wheel. You know those huge hoists that lift a car right up into the air? That's a textbook hydraulic press. A pump creates pressure and oil on a small piston, and that pressure gets transmitted to a much bigger piston that effortlessly lifts a couple of tons. It's perfect. And it's the same exact idea with the hydraulic jack for changing a tire. Every time you pump that handle, you're just applying a small force to a small piston. The jack takes your effort, multiplies it through oil pressure, and lifts the car. It's genius. But maybe the most critical place we use this is the one we don't even think about. It's the system that keeps you safe every single day. Your car's brakes. See, when you step on the brake pedal, you're pushing on a small piston in something called the master cylinder. This creates pressure in your brake fluid.
That pressure then shoots through the lines to much larger cylinders at each wheel, the slave cylinders, and they create a massive clamping force on your brake discs, stopping the car.
And that's the whole point, right there. Your gentle push on a pedal gets transformed into a force so powerful it can stop a 2-ton hunk of metal going at high speed. That is Pascal's principle saving the day.
It's pretty amazing, isn't it? Whether we're lifting a car up or bringing it to a dead stop, the basic idea, the fundamental mechanism, is exactly the same. It all boils down to this one single, really elegant idea.
And here it is, the big takeaway. By using a liquid you can't squish to transmit a constant pressure, we can turn a little bit of effort into a whole lot of power. We use a small, easy force to create a massive, powerful one. That right there is the secret of the liquid lever.
This principle is just a fundamental tool of engineering, built on a really basic property of our world. It kind of makes you wonder, doesn't it? Knowing how this works, where else could we apply this simple, powerful liquid lever to solve some of the world's biggest challenges?